before bringing in numbers into vectors and doing all the calculations, we still want to be able to use vectors in proofs, especially in geometry, and see how, like you would have usually proved equivalent lengths and so on using numbers, we can do the same thing using vectors. So a lot of the examples today are typical examples that are given for vectors in geometry. The idea is to use some of the methods and hints and acknowledge that this topic just requires more practice for you to be able to recognize the tips and the tricks that need to be used to solve them. So there's no clear-cut method for some of these questions, but you can see some of the techniques being used. So we'll start with this. Pause the video, read the question, attempt the questions before I start with the explanation. In here, you can approach these questions differently. You can start defining extra vectors if you need to, but typically you'll notice that we won't need to do that. In here, we're asked to show two things. First, that the M and AB are parallel, and that it's equal to half of AB. Now, going back to the basic definition of vectors, remember that a vector B is parallel to another vector if it's a scalar multiple. So that's if I can show that Mn is a scalar multiple of AB, it means that they are parallel to each other. This is the same thing as saying that AB is double Mn. So you can approach this in different ways. So this is a key point from the previous lesson that we're using. So let's start with actually defining different positions. So I might use a similar method to the book or a slightly different method. They should all be correct, so up to you whichever method is more comfortable, but as long as you're sticking to the correct geometrical and vector methods. So let's say I will define the position A to B as being, I'll define the vector A to B as being A to C plus C to B. Not quite needed, but we can approach that. So I can use this method, and then I could say, well, M to N is half of A to C and half of C to B. Notice how I'm trying to move in the same direction for both of them, so I'm not going the opposite direction. It still works if you want to go opposite direction, but you have to keep it consistent throughout. So after I've done that, I can notice that I can take I can factorize a 1/2 out, and then you'll notice that what you're left with inside is exactly what you had here, which is AB, and we can replace it because we've defined it above, and there you go. So you have Mn is equal to half of AB. So since you can write a sentence here, you can say that since they are a scalar multiple, therefore Mn is parallel to AB, and because of the scalar multiple, Mn has half the magnitude of AB. We are going to do this question, which is another hexagon question, something that was done in the previous lesson, but this time we're not given any positions. So we need to use vectors to prove that same idea, that Mn, so we have this line here, is parallel, so we need to show this line is parallel to this line, and that Mn is equal to 3/2 of AB. So many different ways to approach this. This requires a bit of trial and error, maybe, but the trick is to keep on rewriting things until you get to the equivalence that you want. So let's start with Mn. So I know that Mn, just very basically, is me going to M to E, E to D, and then D to N. No need to go in the center here. We're going to avoid that. So M to E, E to D, and then D to N. And then we're going to start replacing it with actual longer lengths that we can see here. So ME is basically half of FE. And we know that ED, if we look here, ED is exactly A to B. We can go back to basics such as this is a regular hexagon. You have equilateral triangles here. So in regular hexagon, also all the lengths are equal. So ED is equal to AB, same direction. And therefore, they are ED is equal to AB from that fact, back to the definition of equality. So I have that is equal to AB, and DN is half of DC. Once we have that, I can then find equivalences. So if you look here at FE, let's try red. So FE here is the same thing as OD. So now we're going to use the center point. So I'm going to take half of OD. I'm just going to bring this half DC here plus AB. And then I can take a factor of a half out. So I'm left with OD plus DC plus AB. Now, OD and DC, this is using the triangle law where the end point of one is the head of the end of one of your vectors is the beginning of the other vector. Therefore, this is just equal to OC. Okay, go back to the triangle law. You have O to D and then D to C. So I'm picking, let's pick, so O to D, D to C is basically just O to C. You can either deal with this by memorizing the triangle law or by looking at the diagram. So we have this, but I can also see that OC is equal to AB as well, based on the fact that this is a regular hexagon. So I have half of AB as well. So half of AB plus AB will just give you 3/2 AB. And you can use the same conclusion as before. The fact that they're parallel because it's a scalar multiple, and so on. So just use a few minutes to write that extra sentence. In this question, we're given a few numbers, but they're ratios. They're not actual numbers. So what we're trying to show is we're trying to find the ratio to make the two lines parallel. So we're going to use the fact that they are parallel. So we're trying to we're trying to find this ratio. We don't know what it splits into. We know that this splits into, this is a 5 and a 2. We don't know what this splits into. We'll call it A and B here. So we're trying to find what ratio it has to divide S to P in order to make them parallel. So what we're going to do is we know that in order for Mn to be parallel to Qs, there has to be a scalar multiple. So we know that there has to be something and it multiplies with QS. Okay, so that's based on the definition of them being parallel. So we want to get to that. Well, what is QS first? Let's deal with that. QS is basically QP plus PS. Okay, we know that as a fact. Well, what is MN in this case? MN takes 5 parts of QP, so 5 out of 7 of QP, plus I don't know how much of PS, but I know it's gonna be like an A over an A plus B. Okay, so based on that, I need, in order for MN to be parallel to QS, I needed to look something, I needed to look like a scalar multiple of what is above, which we're close, but the coefficients are not equal. I know that they both have to be equal to this lambda. So you can skip the algebra here and recognize that 5 over 7 should be equal to A over A plus B. Or you can go the long route and say, well, I'm trying to get this to be QP plus PS, which using the distributive law, this should be QP lambda PS. And then taking these two together, I can see that lambda has to be equal to 5 over 7 and something like this. So it's a long route only to say that these two have to be equal. And you can immediately see that 5 is equal to A, and the B is going to be equal to 2, and obviously A plus B is equal to 7. So the ratio that N has to divide S to P will be a 2 to 5 ratio. It's a 5 to 2 here, but the question is S to P. So S to P here, it has to divide 2 to 5. So just make sure that you're answering the question clearly. And for the last example, worked example, we are looking for triangles here. So what they're trying to tell you to do here is that all these blue lines in the middle you should be able to construct them such that they also form a triangle. So you get an A to L, and then the B to M. I mean, vector wise and notation wise it doesn't make sense, we're using different letters, but think of the blue lines. They should form a nice triangle. It shouldn't be a weird looking triangle, or it won't close. Well, there's a fact from the previous lesson that we are going to use. It's the fact that it's the definition of the zero vector. If you add up all the lengths of a triangle, they should give you the zero vector. So we know that if I take AB plus BC plus CA, it should give me the zero vector. If you notice, if I take these two using the triangle law, AB plus BC is equal to AC, and AC plus CA is just basically you going the opposite. So it's the same thing as AC minus minus AC, which is 0. So just a mini proof on the side that is the fact that we're using. So if you have 3 vectors aligning like this and giving you a 0, it means that they have formed a triangle. So that's what we're gonna try and do. But first, let's define these 3 lines. So AL is basically A to B plus half of B to C, and BM is B to C plus half of C to A. Careful, make sure you use the correct notation. And then you have the last one being C to N is C to A plus half of A to B. So we want to see that, do they form a triangle? Well, let's add them all up. A to L, B to M, C to N. Just taking all of these, adding them together. And what I'm going to do, I'm just going to skip a few algebraic steps and just combine the like terms together from the beginning, so I can see I have an AB, a half AB here. I have a half BC and a BC. And then I have a half CA and a CA. So just to simplify, I end up getting 3 over 2 AB plus 3 over 2 BC plus 3 over 2 CA, and taking a factor of 3 over 2 out, I end up with these, which if we go back to the beginning here, we know add up to 0 because AB, BC, and CA is the original triangle. So 3 over 2 of the 0 vector is just 0. So we have that these three give you the 0 vector, so they can form a triangle. So hopefully with the videos and the examples, they gave you a good insight into how we use vectors to prove things in geometry. Notice we rarely use numbers unless they showed up as well, so keep that consistent throughout the questions.